Page 6 of Vector Apps Addendum. First thing we're going to talk about is section 15J with angles in space. Take a look at this little drawing here. Basically it shows a plane and a line coming out of the plane. It also has the normal vector, which is perpendicular to the plane. It turns out that the angle between the normal vector and the blue line is related to the angle between the blue line and the plane. So the blue line and the plane have this angle between them, right? And the normal line, the purple, has the purple angle between itself and the blue line. So how are those related? Well, it turns out that the relationship between those two is that, like, look at this. It's a little right triangle here, right? So you can see that the angle theta, which is between the normal line and the blue line, is complementary to angle phi, which is the green angle. Okay, so we can find angle phi by taking 90 degrees and subtracting angle theta. Okay, and of course angle theta we can find by doing the scalar product between the blue and the purple vectors. Okay, so and of course we could do something similar between planes. If we have two normals to the planes and we find the angle between the two normals, then we could pretty much found the angle between the planes also. Because if you have two planes and they're separated by angle of theta, it turns out that their normals, let's draw the normals, purple. It turns out the angle between the normals is also theta. The acute angle between the normals is also theta. Another way of saying that phi and theta are complementary is, instead of saying that cosine theta equals this, we could also say that the sine of phi is this also, okay? Because sine and cosine have, like, of complementary angles are the same, okay? Let's see, number one. Find the angle between the plane and the line. Okay, so to do that, let's first find the normal vector to the plane, which we can see the normal vector of this plane is 1, negative 1, 1, right? And then we're going to find what the direction vector of this line is. The way we're going to find the direction vector of the line is we are going to rewrite it as parametric equations. Okay, so if each one of these is equal to lambda, then the first parametric equation is equal to 1 plus 4 lambda, and the second parametric equation is equal to negative 1 plus 3 lambda, and the last one is equal to z equals negative 2 plus 1 lambda. Okay, so in this case you can see that the direction vector is going to be 4, 3, 1, and if you do a few of these problems you're going to see that you can get the direction vector from the denominators of the Cartesian equation. Okay, so our direction vector for this line is 4, 3, 1. Okay, so basically we need to find the angle between 1, negative 1, 1 and 4, 3, 1, and that would give us the scalar product relationship that we saw before. Okay, so we're going to take the scalar product of these, and that will give us the cosine of theta. So it would be 1, negative 1, 1, scalar product, 4, 3, 1. And then on the denominator, we have the distance of these. So the distance for that one, the length of that one would be square root of 3. The length of that one would be 16 plus 9 plus 1, which would be 26, square root of 26. Okay? And the scalar product at the top would be 4 minus 3 plus 1. So 5 minus 3, which is 2. And the bottom would be 78. Okay? And so the the ratio here, 2 divided by square root of 78 is 0.226. And the angle here would be inverse cosine of 0.226 is 76.9 degrees is theta. In this case, are we looking for theta or phi? Well, we got the plane and we got the line. So actually finding between the normal and the normal vector and the normal vector and the line actually gives us theta. We actually want phi in this case. So we could just say, okay, what is the inverse sine of 0.226? And that would give us 13.1 degrees. Or we could take 90 degrees and subtract 76.9 because they're complementary. That would also give us 13.1 degrees. Okay? Find the acute angle between the planes with equations this one and this one. Okay? So first thing we're going to do is we're going to find the normal vector for this one, which is 2, -1, 1. And then we're going to find the normal vector for this one, which is 1, 3, 2. And then we're going to use the scalar product again to evaluate the ratio between these two. And the denominator would be the lengths of each one. So 4 plus 1 plus 1 is square root of 6. 1, 3, 2 would be 9 plus 4 plus 1, which is 14. And so the top would become 2 minus 3 plus 2, and the bottom would be square root of 6 times 14, which is 84. So it would be 1 divided by square root of 84, which would be equal to 0.109. And since we're finding the angle between two planes, then we don't have to find the complementary angle or anything. We just do the inverse cosine of that, which would be 83.7 degrees. And we're done.